In the next unit, we're going to look at some specific diode circuits and we're going to talk about different analysis techniques. But as sort of a final note in this first unit, what I want to talk about is just some specific types of diodes that have sort of special applications. So the first one is a solar cell. So a solar cell is just a p-n junction that has no applied bias. And so I've got our simple p-n junction drawn down here. Of course, we're oversimplifying, but this is the basic idea at least. So remember, we have a depletion region, and in that depletion region, we have an electric field. So what's going to happen is if we put this p-n junction in sunlight, we're going to have these photons. So we have some sunlight, which is going to be coming into our device, and if it has enough energy for our material, what it can do is it can create electron-hole pairs in our depletion region. So let's make those in blue. So let's say this photon comes in here and it creates an electron and a hole. Well, remember, we have this electric field in this region. So what that's going to do is our electron is going to move this way and our hole is going to move this way. We have some other processes going on once they get out of that depletion region, but ultimately what we can see is we have these charges moving, which means we're going to produce a current. So what we can do then is we can attach an external load, so a light, a heating element, anything you want, and so we can represent that simplistically as a resistor, so let's call that V sub L. And again, if we have holes moving in this direction, electrons moving in this direction, both of those correspond to some photocurrent, I sub pH, which is going in this direction. And of course, that's going to cause a voltage drop across here, and we're going to have power being supplied to this resistor. And so again, this is producing a photocurrent, which we can use to power loads then. So another application, or another specialty type of diode, which operates on the same principles, is a photodiode. So a photodiode, again, is the same idea as a solar cell. So same idea as solar cell, but our photocurrent is now being used to detect an optical signal. So photocurrent used to detect an optical signal. So what we can say is that we can sort of say that this is like converting an optical signal to an electrical signal. So ultimately what we're doing is we're quantifying the amount of photons that are coming into our photodiode. Because of this, this photodiode is going to be operated in reverse bias. So operated in reverse bias, and the reason we want to do that is to increase our detection width. So increase our detection width, or in other words, increase our depletion width here, because that's sort of our sensitive area. And in doing so, we're also increasing that electric field, which means we're going to have more chance of pulling these electrons and holes out of that depletion width before they're able to recombine with other free electrons or other free holes. So again, same basic idea. The main difference is now we're operating it in reverse bias. Of course, there are other structural things that are a little different that we're not getting into. But again, we're going from optical signal input, so optical, we're talking about photons, and we're converting that to an electrical signal.